We present a new technique for simulating wave phenomena such as diffraction and interference using traditional ray tracing technology. These phenomena are due to the phase of interacting waves and are very common in nature. For example, light, sound, and fluid surfaces all exhibit these phenomena. We introduce bidirectional scattering distribution function, the BSDF, with positive as well as negative coefficients. These BSDFs are calculated using the microstructure of the material. The generated BSDFs can simulate waves using existing ray-based methods. The intensity of the reflected or scattered rays indirectly encodes the phase of the wave, conveniently allowing interference after multiple bounces within a traditional rendering framework. Although our method is based on rigorous Fourier optics theory of microstructures, our implementation abstracts away the complexity of phase-based calculations. Rendering simply requires our smarter BSDF. Our method requires minimal changes to achieve global illumination effects using standard software, like PBRT. The Wigner distribution function describes how a set of parallel rays will be transformed after passing through an occluder transparency. We modify the Wigner distribution function to deal with reflection, transmission, emission, and absorption. We combine the scattering predicted by the Wigner distribution function to derive a BSDF from the geometric microstructure of the material. Although the Wigner distribution function only predicts a 2D function at a point, we derive a 4D BSDF by shearing in the incoming-outgoing space. For an illustration of this idea, let's consider rays in a differential neighborhood one at a time. These BSDFs allow reflected rays with negative intensities. When a positive and negative ray combine after multiple bounces, they automatically simulate destructive interference as out-of-phase waves. Our representation preserves non-negative radiance under integration over incoming rays. This example shows a CD lit by a flashlight, creating a rainbow effect on the diffuse wall. We use photon mapping to create second bounce lighting. Other than allowing negative values in the BSDF, no changes were made to PBRT or the photon mapping code to generate this image. We demonstrate its physical accuracy by modeling a transmission function for light passing through a rectangular aperture. We compared the rendered result with the calculated Fraunhofer diffraction and found an error of less than 1%. A previous method, called optical path differencing, involves keeping track of the travel distance in order to calculate phase information. Unfortunately, this technique requires modifications to traditional rendering systems. In addition, it does not allow the use of importance sampling. This makes it computationally expensive. Diffraction shaders remove the need for phase tracking and create instantaneous interference at the point of reflection. This creates realistic one-bounce effects, assuming light and observer are at infinity. However, it ignores interference effects involving rays arriving from different directions. This situation arises in near field when simulating light and almost everywhere when simulating acoustics. Observable light fields and augmented light fields are new concepts in computer graphics that also use the Wigner distribution function. But we use it not for propagation, but for creating new material reflectance coefficients. In acoustics, diffraction is often performed around edges for efficiency and speed. Such techniques, however, ignore mid-air diffraction and may miss some spots. We utilized optimizations such as lookup tables and importance sampling to efficiently render the image shown here. This also allows for real-time rendering of single bounce diffraction on the GPU. Our technique can also be used to render holograms as a material BSDF when the structure of the holographic film is known. Our technique can also be used to model camera optics to obtain the point spread function of a point for a given camera. Camera optics is a near-field effect because the aperture size is comparable to the propagation distance. It greatly benefits from importance sampling of outgoing rays. We can use this to prototype new camera systems. We can accurately predict the effect of aperture and f-stop.